Okay, let's do more unbounded operator theory. So we have been discussing about densely defined operators, then its adjoints. Then we talked about the closed operators, and something is densely defined, then it has an adjoint. Okay, and what else we prove? Something is closable if and only if its adjoint is densely defined. That's what we prove. Okay. And we say something is self-adjoint if T equal to T star. That means the domain has to match and the operator has to match. So, but we usually will say definition, T is an unbounded operator. T is an unbounded operator. Okay. Then T is symmetric. We say T is symmetric if T is contained in T star. T is contained in T star means, so domain of T is contained in domain of T star, and T star restricted to domain of T is T itself, okay, is equal to T. Okay, that is domain of T is contained in domain of T star. T star domain can be bigger than this, and T star restricted to domain of T is T. That is, it satisfies this property. Txy equal to xty. That's all. This is the property it satisfies. So this is what symmetric means. Symmetric means Txy equal to Txy for all x and y in domain of T. That's all. Okay. There may be more y. I mean, this is the property of the adjoint. I mean, so self-adjoint kind of thing. T need not be self-adjoint. Okay. Symmetric does not mean self-adjoint. Symmetric just means T is contained in T star. Okay. So if T is equal to T star, that is domain also match. Okay. So a symmetric operator is self-adjoint if and only domain of T is same as domain of T star. That's all. Okay. If then we say it's self-adjoint. Then we say T is self-adjoint. So self-adjoint means the domain should also match. Okay. T symmetric. If we take a symmetric operator, then T is self-adjoint if domain of T is equal to domain of T star. That's all. Okay. I will give you an example. You take H is equal to L201 and taking the open interval. You can take closed interval also. L201. Okay. L201. It doesn't matter. When you take L2 end point, 1 point, single point doesn't matter. L2 is defined up to almost, it's defined almost everywhere. It's not defined everywhere. So you take L2 of open interval or 0, 1 doesn't matter. Of course, for continuous function, it matters. Usually we'll take continuous function on compacted, so that is different. Okay. Now you define an operator T. So domain of T be equal to all F F in. See, this is C compact of C01. That is, sorry. And for differential operator, we need to have open sets, no? C01. That is different C1, 01. Differentiable in 01. Okay. And compactly supported. That is, there exists an open interval inside. Sorry, there is a closed interval AB. 01 is not compact. Okay. So they're compactly supported. So there exists an open interval AB in 01 such that F restricted to this AB, this complement is 0. Okay. I mean, between 0 to A and B to 1, it is 0. That's all. Okay. It's supported in the closed interval AB, compactly supported. Okay. Now define T of F is equal to I times F prime. I need this I to make it self-adjoint, otherwise it will be kind of T will be minus T star or something. So that's why I put an I. TF equal to IF. Okay. Then you can find that then T is symmetric.
What is that IF prime?
I times F prime. I is the I is minus 1. Derivative.
Oh.
It's differentiable. That's why it's
the real value.
huh?
Are the real value function?
No, complex valued function. You can take derivative. It's just one variable function. It takes values in complex plane. Okay. I mean, we consider only complex spaces, Hilbert spaces. Okay. Otherwise, there will be problem in the spectral theorem and other things. This complex real field is not algebraic closed, so there will be a problem somewhere. I mean, its roots will be eigenvalues will be in complex plane or something, so it will be a problem. Okay, so.
And then the spectrum will be empty.
Something correct. Spectrum will not be empty when you take the complex field. That's the main thing. So T is symmetric. Why is T symmetric? Can anyone say? You can write it and tell me. You can write it and tell me why is T symmetric? 5 marks.
Integration by parts.
Super, good, correct. That's all. And it's 0, takes 0 value in the end point. So that's all. Okay, so integration by parts. So if you want to talk about TFG, which is just going to be integral FG prime, right? Now F prime G, F prime G prime bar, F prime I times G prime G bar, right? G bar.
Okay. It should be conjugate linear in the first variable.
Which is conjugate in the first variable? It's all linear. I just multiplication by I. There's nothing conjugate.
It should be IF prime bar.
No, IF prime?
Because TF is the first.
Okay, sure. Because I have taken the because this is specifically rated. Otherwise, you should take minus I there. So this is because our course, yeah, it is correct. Our inner product is we are still working with this quantum thing, no? So because of this, yeah, it's conjugate linear in the first variable. Good. Yeah, it is a bar in the first variable. Correct. Now this is equal to integration by parts, 0 to 1, of course. So if you take the FG, that other whatever that scalar part will come, that will be 0 because it vanishes in the end points. So this is equal to integral. You take the which is same as I mean F bar, sorry, G prime, and you can take the I here, right? Is that right? I of bar, so minus I will come out. And there is a minus sign, no? Integration part will get a minus sign. So because of that, this will go. Here it is like this. And here it is. So this is integration by parts. So that's why T is symmetric. So it satisfies this condition, T is symmetric. So what would be the adjoint? Adjoint can be very big. I mean, there is something called absolutely continuous functions. I will not go through this. If you are interested in the measure theory book by Sundar, there's a chapter dedicated to this. This fundamental theorem of calculus, which there is a measure theoretic version of that. Okay, this instead of you can take derivative in many sense, a kind of distribution, something absolutely continuous function and other things. So it's so the F star domain of F star is sorry domain of T star will be all absolutely continuous. I mean, absolutely continuous function on 0, 1. Okay, whatever, absolutely continuous function. Continuous functions in 0, 1. So they will have a derivative. That you can make sense of a derivative using integration. It's not usual derivative. You know, you don't take the limit. It will satisfy the integral condition. Derivative fundamental theorem of calculus. So I can give you the intuition. Fundamental theorem of calculus say derivative. If it is derivative, then something is satisfied. Something similar will be satisfied. It will be of a integral of some function like that. Okay, so it will look like that. So then that derivative, whatever that derivative, will be the T star. Okay, T star is actually equal to IF prime. But this is the measure defined through measure theoretic. Okay, this is the generalized derivative. Which you can define through distributions, I think. Okay, there is a course in harmonic analysis or something. You can define distribution. So through distribution, you can define this. Okay, so T star will be that. So T star is almost like T, but the domain is much bigger. Okay, and there is no condition. See here, the condition is it vanishes in the compact set. Or you can even say T to be. I mean, you can take a different operator. I am not very sure, but if you take absolutely continuous function vanishing at 0 and 1, then I think T equal to T star. Is that right? If it vanishes on both points, T equal to T star. I'm not sure. I have to. I don't remember. Okay. See, if you can define that same IF prime. But still, you can see that the reason for T star is you can take any absolutely continuous function. It satisfies this. And even though G does not vanish in the endpoint, F vanishes in the endpoint. So whatever the bracket will go away. So this formula is still true by integration by parts. Okay. So that is why T star is there. Okay. Anyway, these are all some unrelated. I just want to give an example. Oh my God, I want to prove something, but I may not be able to finish it. Okay. If you don't mind, I will finish it. Okay. I want to prove the following theorem. This is Tauer's spectral theorem for that. Okay. This is the proposition I want to prove. Okay. T is symmetric. So it is, in general, it is difficult to determine whether T is self-adjoint. See, if you have a small T with a small domain, T star will have a very big domain. Okay, that's what T star is. If you increase the domain of T, then the domain of T star will decrease. At some point, they have to coincide, something like that. Okay, that is why I said if you take this kind of compactly supported differentiable functions, the T star is too big. That's the most general T. Okay, but if you take some absolutely continuous function vanishing at things, that are something. But there at some point T will be equal to T star. You go on reducing it. It's the same kind of everything is defined through this IF prime. I mean, if you look at functional, whatever the symbol wise, it's the same thing. Okay, it's just the domain will vary. At some point, it will become T equal to T star. Okay, so we want to determine that condition. Okay, so we want to determine a condition for that. So maybe using that condition, we can verify whatever I said is true or not. Okay, so this is the condition. Phi is symmetric. Then the following are equivalent. 1, T equal to T star. Okay, 2 is equivalent to saying T is closed. Of course, T equal to T star means it is closed. And kernel of T star minus Z equal to kernel of T star minus Z bar. I mean, you can just take I, okay? I mean, the imaginary number I, it is enough. But I mean, but we can take general Z. We will use it for just I, okay? Equal to 0 for all Z in C minus R. That is imaginary part of z is not equal to 0. Okay. All non-real complex numbers, z is non-real complex numbers. The kernel of t star minus z, t star minus z bar is 0. Trivial. Okay. You know what is kernel? Kernel is of course not defined on every operator. Kernel, it is all those elements in the domain which vanishes. Okay, of course. Otherwise, it's not defined. Okay. This is equivalent to saying range of t minus z equal to range of t minus z bar equal to h. Of course, kernel range is the image of t minus z, the image of t minus z, image of domain of t minus z under t minus z. Okay. I mean, otherwise it's not defined. So those, I hope those things are clear. I don't know how to write. Usually kernel means you will just write it, but here you have to take care of the domain. Okay. All those elements in the domain which vanishes for t star minus z. Okay. And the domain of t star and domain of t star minus z are same. Okay. Because that is the intersection. The domain of z is just multiplication by z, which has the domain, which is a bounded operator, domain, everything. So that intersection of the domain, it's it's just the intersection of them. So it's okay, proof. Let us see how much we can prove. 1 implies 2, that is t equal to t star. We are assuming t equal to t star. Then of course t is closed. This implies t is closed because any star is closed. Okay, any self-adjoint star is a closed operator. We have proved that. How did we prove? We proved that the graph is kernel of perp of something xtx, right? Minus xtx something. It's a perp of that. We proved it theorem. If you remember, it's a perp of some subspace. Okay. We make a flip on the graph of t and then take the perp. Okay. Minus times flip. Xy going to y minus x. Okay. And then take the perp. You apply that on xy. I mean, if you take the unitary operator on the graph, xy going to minus x y minus x. Okay, this unitary operator. This you call it as u. U of the graph of t. Perp is equal to graph of t star. We proved that. Okay. Since it's a perp, graph of t star is always closed, and because of that, t star is closed. So t equal to t star means t is of course closed. Okay. It's a closed operator. Okay. Now we have to prove that the kernel of t star minus z equal to kernel of t square. Now let x is in the kernel of. See, this is finite dimensional. There is nothing to prove, no. So not finite dimensional. For a bounded operator, there is nothing to prove, no. If it's t is a bounded operator, this just says z is an eigenvalue of t. Then wait. Oh, it doesn't say. Sorry, it doesn't say anything. Here it will say. Okay. So okay. I mean, here it says that. So let x is okay. Let's do it. X is in the. No, it doesn't say anything. Kernel of t star minus z. Okay. Let x is in the kernel of t star minus z. Okay. Then we want to prove x is equal to 0. Okay. So norm x square equal to, we will prove norm x square equal to 0, which is xx. Okay. And z is not equal to 0, of course. Z is not equal to 0 because it has a non-zero imaginary part. So it's not equal to 0. So you can write it as 1 by z, which is equal to z bar, our conjugate linear in the first variable, zxx. Okay. Which is equal to, but it is in the kernel of that. So this is equal to t star x. And t and t star coincides. Okay, we are assuming t equal to t star. Okay. 1 over z bar. No, I want to take 1 by z into z bar. That's okay. Let's take z. Okay. Which is equal to t of x. T equal to t star. Okay. that is equal to x tx, which is equal to t equal to t star, since t equal to t star. Okay. And that is equal to, there you will get z. X, zx, z bar x. Yeah, which is equal to z bar xx. Okay. So since imaginary part of z is not equal to 0, so I divided 1 by z for some. I want to take it as z, but I am writing it in this form. It's okay. I want to take z1 inside that, that's why I wrote it. Now it's okay. So this implies x norm x square equal to 0. Because the imaginary part is non-zero, so because of that it's norm x equal to 0. Okay. So that implies kernel of t star minus z is trivial. Okay. The same proof for z bar also. There is nothing. Z has, I mean, I have used the fact that Z has non-zero imaginary part. Z bar also has non-zero. Same true. Similarly, kernel of t star minus z bar is also equal to 0. So the proof is over. So we are assuming t equal to t star. Then we proved that kernel of t star minus z, t star minus z bar is 0. Trivial. Direct. Okay. Now we assume 2. That is, we are assuming t is closed and kernel of t star minus z, t star minus z bar is 0. Then we want to prove the range of t minus z, range of t minus z bar is h, everything. Okay. So for the
in the statement, like kernel of t star minus z is trivial, isn't for all z non-real. So isn't that directly imply that t star minus z bar, the kernel of that is also trivial because it's for all z non-real. Like why do we write it in the statement?
That's right. For some z or some dz or we have proved for all z, no?
So you needed imaginary part to be non-zero. We needed imaginary part to be non-zero.
Correct. No, he's just saying t star minus z is not equal to 0 for z imaginary part not 0. Then certainly it implies. Now, if you are proving it for any z, so it is clearly true. That is right. I'm just wondering whether I made a mistake or not. I say proof, there is no problem with the proof, so it's okay. Yeah, I think so. You don't need to prove it for the other one. No, the proof, there is something called Cayley transform. It is just t star minus I, t star plus I. We just have to use. Okay. So, yeah, what you are saying is true. I just use a general result. Yeah.
So we don't need to.
Yeah, we don't need to prove. Yeah, the other statement is not needed as far as I see. For the next one is also, I don't think it's needed. Yeah. But is it no? It is enough for one z, I think. I mean, to get the first statement, the range of t minus z equal to range of t minus z bar. Some one single z. Such that z, the imaginary of z is not equal to 0.
There exists such as that.
Yeah, there exists a z such that this happens. That is enough. Okay. We will prove it. In the proof, you will see. Okay. Yeah, this is true for all z, correct. Once we have it, then it is true for all z, such that imaginary c is not. I mean, here also the z satisfies that. Okay, maybe there exists in z. Okay, I'll just there exists in z. But then we have proved for every z.
So maybe we can just add a fourth statement saying that these closure kernel of like for some z this thing moves. So
Say it again. Yeah. Sum is equivalent to all, you are saying.
So we can deny the statement.
Yeah, correct. Yeah, something like that. Yeah. But anyway, we are going to use for z equal to I. Okay. So that will. Yeah, you are
The third statement, is it the third statement?
Yeah, third statement also is it is non-real.
For all z.
No, is it in C minus R?
Like for all z non.
Correct, all z non-z. But it's to prove 3 implies 1, it is enough for 1 z. Okay. It's enough for 1 z. Yeah. Okay. Anyway, I'll. Okay, yeah, I think so. So, should I write it again? So, okay, there exists a z. Okay, but it follows t is closed. This is equal to this for all is for all is it. Okay. From that it follows. Such that this happens. Okay, then it is true. Let us, as he said, let us use that statement. Okay. There exists a z such that, but then we need it for both z and z bar. There exists one single z. So then from that you will get the first statement. First statement implies for all z. Okay. If it is true for one z, it is true for every z. Okay, that's what this says. That's what it means. Okay. So let us see the proof.
So there should be like two equivalent mode statements. It's a counterpart to two. And
Correct.
They
Yeah.
exist.
Yeah, correct. Yeah. Yeah. 2 implies 3. Yeah. Possibly there exists a z such that kernel of C. Now I am assuming that T is closed and there exists a z. I mean, there is a counterpart. 2 prime or something. Okay. 2 prime is, see, this is for 2 is for all, is it? 2 prime is there exists a z. Okay. Then I prove for there exists a, but then if it exists for some z, for the same z, the statement 3 is true. Statement 2 and 3 are equivalent for that z. We have to write too many statements. It's all not needed. Okay. These things are not useful. As I said, we are going to use for I. Okay. So 2 implies 3. So the statements are T is closed. And kernel of T star minus Z equal to kernel of T star minus Z bar equal to 0. Singleton 0. Okay. Then, see, this is another exercise. Kernel of T star equal to yeah, but kernel of T star need not be closed here. It's unbounded operator. So we should be a bit careful. Kernel of T star per equal to range of T closure. Okay. Because it's unbounded operator. So kernel of T star, kernel need not be closed. Will not be closed. Okay. I mean, mostly. So it will not be closed. So, I mean, in fact, for a linear functional defined on something, it's closed, it's bounded if and only if kernel is closed. The other way is also true. Okay. So, yeah. So kernel of T star perp is equal to range of T closure. Okay. Now we have kernel is trivial. Okay. That means the range. Okay. So this is an exercise. Okay. The same. I mean, there is really nothing in this. Something in the kernel means what? Kernel of T star. Perp means what? X of T star Y equals 0. That means Txy equals 0. Right? So Y is in the, yeah, it's about that. So X is in, yeah, what are we assuming? X is in the kernel T star perp. Okay. So that is X is orthogonal to T star kernel, sorry. The X is range of T. I should have range. Then I should have T star here. Okay. But y is densely defined, right? I mean, y is, see, x is orthogonal to range of t. That means t star x y equal to 0 for all y in domain of t, which is dense. Okay, so t star x has to be 0. And x is in the domain of that, right? You have to be carefully write it. I think this is the equation x ty equal to 0. What do we have? If x is in kernel of t star, that means x is in the domain of t star and x is in x, I mean, then t star x equal to 0. Okay. So anyway, you write the exercise. Okay. It will give you carefully write the exercise. Okay. It's an exercise. Okay. So now this implies we know that kernel of t star is trivial. Okay. Then the range of t is dense. Okay. So this implies, so 2 implies 2, we are assuming kernel of t star is so range of t minus, say the bar of t star minus z, the bar is t minus z bar. Okay, I'm using the other one, t star minus z bar. So range of t is dense. Dense in H. Okay. So we need to prove that we only need to prove range of t minus z is closed. Okay. We need to prove it's closed. If it is closed, then it will be everything. So let xn, so range is closed. So let's see. Let yn contained in range of t minus z. Z or z bar. I mean, same thing will work for z bar also. Okay, there is no difference. Z. Okay. And yn converges to y. We need to say that y is also in the range of t minus z. That's what you have to say, right? We want to prove the range of t minus z is closed. So suppose yn is some sequence in range of t minus z. We need to prove yn converges to y. Sorry, we need to, and yn converges to y. We need to prove that y is also in the range of that. That's what we have to prove. That is yn is equal to t minus z xn with xn in domain of t. Okay, domain of t minus z, domain of t is same. Okay, t minus z. This converges. So okay. Now I want to prove that xn is Cauchy. Okay, then it will have a xn is Cauchy, so it will converge. Okay, but we are assuming the operator is closed. Operator is closed means xn converges to x and t minus z. T is closed, so t minus z is also closed. Okay, t minus z xn also converges to something. Then xn has to, the limit has to be in the domain, and t minus z. That is the definition of the operator being closed. Anyway, I will write it again. Okay. Now I want to prove that xn converges in H, need not be within the domain, which will follow because the graph of t is closed. Okay. So how do I prove? Now norm of t minus z, let's say some z. Okay. Let's compute it for z, some z. Square. So let z is equal to x plus iy. There is already x and other thing. So a plus ib. Oh, there is already z. Okay. So let us use some z. Okay. And z is equal to a plus ib. Okay. Xi is a vector. Okay. I mean, I don't want to write xn. You can write xn minus something for a general vector. Okay. This is equal to, so t minus a plus ib, right? Minus ib. Okay. So this will be norm of t minus a xi square plus I square will go away. So B square will come out times B is real times norm xi square plus real part of 2 times real part of real part of t of t minus z t minus sorry a xi ib xi, right? Correct. Okay. Now t is assumed to be symmetric, right? We are assuming determining when a symmetric operator is self-adjoint. Okay, that is what we are assuming. Okay, t is assumed to be symmetric. So you can, and a is real. So t minus a is symmetric. You can take t minus a to the other side and bring this ib to the other side. It will become minus of that.
So how do we know T is symmetric?
We are assuming t is symmetric in the proposition beginning. We are only determining when a symmetric operator is self-adjoint. We are not, it's not a general statement for self-adjoint operator. We are assuming t is symmetric. Okay. So since t is symmetric, so you can take t minus a to the other side and bring ib to the side by minus I. So this will be 0. This part, I mean, there is no real part. This itself will be, this itself is 0. That is t minus a xi ib xi is equal to minus, if you, I mean, which is equal to ib, I can take it out, minus ib, I can take it. Forget about I and b. This is true. Okay, I is just a number. You can just take it out. Okay, times xi into t minus a xi. Okay. Okay, this is real, so that will be purely imaginary. Real part is 0. Okay. That, so this is equal to 0. Okay. Yeah. So this implies t minus z xn minus xm, right?
Why is this real?
Because ib is there, no?
Okay.
ib you can take it out, and then t minus a xi is real because that is equal to this. That's the problem. T minus a xi equal to xi t minus a xi. So this is real. ib is just a scalar. You can take it out. So that whole thing is imaginary. So that is 0. Okay. So this is equal to, what we get is t minus something, some number. This is greater than or equal to b square times xn minus xm whole square. Okay, I just removed the, I'm just using this stuff. Now we know that this is our yn minus ym. This is equal to yn minus ym square. This goes to 0. So this should also go to 0. This, I mean, this implies xn is Cauchy. So xn converges to x in h. But since t minus z is closed, okay, x is in domain of, or if you want to go through t and other things, okay, doesn't matter. Domain of t minus z, and t minus z of x is equal to y. This implies y is in the range of t minus z. That's what we want to prove. We want to prove the range of t minus z is closed. We took a sequence in yn, and we want to, and if it converges, we want to say that the limit is also there. Okay, so this, we proved that y is in the range of t minus z. Okay. So let go. Want to see something before? No, this is fine now. So we proved that range is closed. Similarly, we prove for T minus Z bar also. There is no difference. Okay. It is just that we have used the fact that imaginary path is not equal to 0. Okay, because we need that B outside. B is not equal to 0. Okay, we are using that B. Okay. I am past 10 minutes. So I will prove the last part next class. Okay. It doesn't take much time, but still